Welcome to this video lecture. My name is Mark Scythian, and the date today is April 26, 2025. So this video is going to focus on gas, liquid, and solid equivalent mass acceleration. So most understand accelerating mass such as water or liquids and solids, the force, and the correlating mass times acceleration, and the equal and opposite reactive force. So one can quickly posit the acceleration of tangible matter such as liquids and solids, but for some reason when it comes to gas propulsion, many but not all seem to be a bit confused because it's not as tangible as liquids and solids. So when dealing especially with acceleration of gases for, let's say, practical applications such as thrust, jet propulsion, etc., all you need to do is calculate the atmospheric pressure based on a certain elevation above mean sea level. So we have 761 feet above mean sea level, and then an air temperature of 63 degrees Fahrenheit. So those are the first two data points to access. Then you can use this formula here. This is a atmospheres formula in chemistry. So this is just the feet above mean sea level divided into this constant here. This ratio subtracted from 1, and then whatever answer you equate, you take it to this 5.255876 power, and you'll calculate then the atmosphere. So it should be like 0.97 something, and then you multiply that coefficient atmospheres times 14.7, the sea level standard atmospheric pressure, and so you calculate 14.3 psi. If you take the 14.3 psi and multiply it times the molar mass for air, 29 grams per mole, and then divide it into the product of the ideal gas law constant for air, which is 10.73, times the Rankine absolute air temperature, so 63 degrees Fahrenheit plus 460, you will then be able to calculate the air density in pounds per cubic foot. So if you find its inverse, 1 over the air density, this will calculate the cubic feet required to equate 1 pound of mass air. So weighing 1 pound of air, it is 13.5 cubic feet at 63 degrees Fahrenheit air temperature at 761 feet above mean sea level. So if you multiply, let's say 10 pounds of air, it would be 10 times 13.5. So 135 cubic feet of air is equal to 10 pounds of mass air, as in the weight of the air. So if this propulsion device had accelerated 10 pounds of air per second over 1 second, so it is an acceleration of, let's say, 550 feet per second acceleration per 1 second, and that is 10 pounds mass air accelerated per second, we could simply use the propulsion equation, and that is just the final velocity times the pounds per second mass airflow divided by gravity in the US system of measurement, which is 32.2 feet per second squared. So this is 170.8 pounds thrust, but it first starts in the rear direction, and then that is the force incurred. Thus, a reactive force in the opposite direction called thrust takes place. So that's Newton's third law of motion, taken from the forces mass times acceleration equation in Newton's second law of motion. So we have proven that 10 pounds of mass air, or 135 cubic feet of air at an air temperature of 63 degrees Fahrenheit at an elevation of 761 feet above mean sea level? If so, will yield 170.8 pounds of thrust. Now, that is tangible by calculation and then design, and of course a solid structure would have to be created, like the propulsion device and the fan blades and the motor and everything, right? So we could narrow down 135 cubic feet of air as equal to 10 pounds of mass air, of course in an air temperature of 63 degrees Fahrenheit, 761 feet above mean sea level. So I'll just put those down as the reference point for gas, mass acceleration of a gas. Okay, so call that air. And then next one, we compare it to water, a liquid. Same thing, 10 pounds. So we know the density of water is 62.4 pounds mass per cubic foot volume. So 10 divided into 62.4 is 0.16 cubic feet of water if accelerated out of, let's say, a hydrojet from rest to 550 feet per second, and that's 10 pounds mass water flow per second. We would also have 170.8 pounds force of thrust in the equal and opposite direction. And then the last one everybody should pretty much get, that would be comparing the gas, air, and the water liquid. Of course, I got the colors reversed, like green water. No, it's blue water, but I wanted to make it a little memorable. So imagine you have a green ocean and green sky, or water's, water's supposed to be blue, but I put air as blue this time. So we don't have a green sky, do we? So, okay, we have final velocity. So assume all three have just the final velocity of 550 feet per second, mass per second of 10 pounds, and then thrust / recoil 170.8. And okay, so we have that air. We did water. So the last one we will do is a 10-pound brick that's accelerated from rest to 550 feet per second in the time span of 1 second. And that's pretty straightforward. If you accelerate this brick somehow through a sling or a rail or whatever, you throw it hard enough, but you get the final speed to 550 feet per second in the acceleration time of 1 second. So I'm assuming 1 second, so we can just test it. So we could say this is a solid mass object, also 10 pounds, which is equivalent to 0.16 cubic feet of water or 135 cubic feet of air. So we can just check and see if that's actually true. The final velocity of 550 feet per second in 1 second. I'm assuming it's 1 second, but we can always verify with a solid material if our force divided by mass or acceleration is a time function of 1 second. So what do we get here? 4.45 newtons force is equal to 1 pound of force. So we could take the 170.8 pounds force and multiply it times 4.45 and then convert the 10-pound weight into kilograms mass, so 10 divided into 2.2, and then make this then a calculation of 167 meters per second squared acceleration. And then we know acceleration is velocity divided by time, so we could flip it around, so it is time is equal to velocity divided by acceleration, v over a. And so we have final velocity of 550 feet per second, but we got to convert it to meters per second. So we actually divide 167.7 into 167 meters per second squared. So it's approximately 1 second. It's 1.0003 something, right? So 1 second, we've proven that. So now the main takeaway is that you're dealing with, let's say, kinematics, dynamics, projectiles, water jets, etc., solid and liquid propulsion. And now you have to get into gas propulsion. And some students, some people, some researchers are kind of perplexed, like, how do you quantify the air? Well, treat the air like you would any liquid and any solid. It's still mass, isn't it? So based on this lecture, you can conclude that 135 cubic feet of air volume at 63 degrees Fahrenheit and 761 feet above mean sea level, 0.16 cubic feet volume water at room temperature, and a 10-pound brick are all equal weights. And thus, if these are accelerated from rest to 550 feet per second, final velocity in an acceleration time of 1 second, the recoil force or thrust of all of these will equal 170.8 pounds force. So that's relevant to the projectiles, jet propulsion as in gas propulsion, and of course the hydrojet. So it could split the mass into gas, liquid, and solid, and then acceleration is the change of velocity over time. Thank you for watching this lecture video and have a great day.